Okay, so this is the second part of the wave video, but before you watch this video, please watch the first part of the wave video for those of you who have missed the lesson on 30th October. Okay, I will also be doing a very quick recap before I start on the second part of the video. Okay, so recap is the first thing is you need to know what are waves. Okay, so what are waves? They actually transfer energy from one point to another by vibration. Okay, and we also talk about the particles in the medium. That means so how vibration actually causes the wave to transfer this energy. Then second thing that you need to know is the types of waves. Okay, so for general wave property 1, it is talking about mainly on transverse waves. Okay, then the second part will be longitudinal. Okay, then for transverse you must think of the keyword called perpendicular. Okay, later I'll elaborate. For longitudinal you will think about parallel. Okay, that means the directions are parallel. For transverse, the directions are perpendicular. So in order for something to be perpendicular to another thing, there must be two directions, right? You cannot just be perpendicular to yourself. So later I'll elaborate. Then you also need to know the examples. Okay, for longitudinal, it is sound, right? So very quickly, you will know that if a MCQ comes out asking you to list what are the to choose the options that has waves that are transverse and longitudinal. Once you see sound, you'll know that it's longitudinal. Okay. So transverse is, just now I was talking about perpendicular, the direction of wave propagation. That means the wave motion is perpendicular to the direction of vibration of the particles in the medium. Okay, in the medium. Right, then for longitudinal you just switch the directions to parallel. So just take note that for transverse is perpendicular, wave direction is perpendicular to direction of vibration of particles. For longitudinal it is parallel. Okay, okay, you also need to memorize what is the definition for wavefronts. Okay, so wavefront is an imaginary line that joins all adjacent points on the waves that are in phase. Okay, so later we'll talk about what is in phase. Then the motion of any selected point in a wave is periodic and repetitive. Periodic, we first heard this term in a pendulum, right? That means it follows a certain time to complete one oscillation. Okay, so waves transfer energy without transferring matter. Okay, so this is part B of the success criteria. There's this part here that you need to know. It has been talked about a lot in our first video. Okay, so basically, if I were to draw a wave, okay, and this is a transverse wave, and let's say the wave is going in this direction, example, wave direction. Okay, so for the particles, right, they will not be going in the same direction because this is a transverse. So when I talk about transverse, what do you think of? You think of the word called perpendicular. That means if the wave direction is from left to right, in order to be perpendicular, the particles must be moving up or down. And we do know that the particle at the highest point, incidentally, it is called a crest. The particle at the crest will definitely go down because it is already at the highest point, right? It's already at the highest point. Then the particle at the trough, which is actually the lowest point, okay, since it has already reached the lowest point, the next motion is going up. You see that although the wave is going from left to right, the particles are moving up and down, perpendicular to the wave direction. Okay, so for these two particles, and in fact all the other particles on the crest and on the trough, we know that what is the next motion? It should either be up or down, right? This is quite common sense. But sometimes the question will ask you, for example, this particle. Okay, so for this particle, we will not know at one glance immediately whether is it going up or down. Okay, so there's a certain technique. Okay, so the steps are listed here. Number one, know the wave direction. In this case, our wave direction is going to the right, left to right. Okay, step 2 is a little bit harder. You must draw the next wave according to the wave direction. Okay, meaning I will, with a dotted line, I will draw the next wave. Okay, in the direction of the wave motion. The wave is going from left to right. So meaning I will see the wave shifting to the right. Okay, shifting to the right. Okay, because the wave is going left to right, I'll see the wave shifting from to the right maybe a short time later. Okay, so I just sketch. And step 3, draw a vertical line from the particle to see where it intersects with the next wave. Okay, so just now we talked about particles at the crest and particles at the trough. Particles at the crest definitely will go down. Yes, it will go down. Okay, so basically you draw a vertical line downwards, and where do you see that it cuts the dotted line? It actually cuts over here. Yes, it cuts over here. From the highest point, it moves down to a lower position. So it coincides with our theory that when you're at the highest point, next motion you're going down. Okay, let's test it for the particle in the trough. Okay, so again we draw a vertical line, and where does it cut the dotted line? Somewhere here. So initially it was here at the lowest point, then it actually moves up. Okay, so with this we know that the technique is correct. Okay, and if I were to draw a vertical line at this particle position, the green color one, we know that it will cut the dotted wave, the one that is happening a while later, moving to the right. It will cut this wave at this position. So initially it was here at 1. Okay, then it moved up to 2. That means its next motion is going up. Its next motion is going up. Okay, let's choose another point. Maybe this point. Okay, it's also on this position whereby we are not very sure whether it will go up or down. Okay, and since we have already drawn our wave, the next wave according to the wave direction, and then we draw a vertical line downwards, or we draw a vertical line, it actually cuts the dotted line, the next wave line, at the bottom position. So I know that it is going to move down. So as you can see from the green and the red and the black dot, although both are in the same position at this time instance, okay, the green dot actually moves up, the black dot actually moves down. So this is a technique or step that you need to take to see whether the particles are moving up or down in the next instance. Okay, so you can actually try B1 and B2. The answers have already been talked about in my previous video. Okay, next, compare transverse and longitudinal wave and give examples of each. This one quite simple. Yeah. Okay, so now I also talk about DD graph, displacement distance graph, in my previous video. Okay, so I'll just quickly do a recap. So displacement distance, as the name suggests, DD graph. Okay, not your PDD. Your DD graph is actually made up of D displacement in the y-axis, okay, and your distance in the x-axis. So I mentioned before that this graph is not like your kinematics graph whereby you need to find gradient or area under the graph. This one is actually very simple. Okay, so each axis serves its own purpose. The y-axis will tell us the displacement, x-axis will tell us the distance. Okay, but before we go into the graph, let's go look at some technical term. Just now I already introduced what is crest. It's actually the highest point in a wave. Okay, so examples A, B, and Okay, I think I accidentally pressed the pause button. So now I sort of have to restart. Okay, I don't know whether you have heard me talking about DD graph. Y-axis is displacement, can get amplitude. X-axis can get distance, which is the wavelength. Okay, so please watch my video 1. Okay, now I need to go to the start of this video, which is actually talking about DT graph. Okay, so for DT graph, as I've written over here, the y-axis is again displacement, so I can get amplitude. X-axis is time, okay, which means I can get period. What is period? Over here it says that period is the time taken by each point on the wave to complete one oscillation. Okay, that means I need to know the time. I can get the time taken to complete one oscillation. Okay, so I think this part was lost in my so I'll just talk about it. If I were to start from here, okay, how does this wave complete one wave? Okay, it will have to go to the highest point, okay, come back to its same position as before, but it has to go to the lowest point and then end up back in the same place as it was. Okay, so this is the particle. But what if I were to start at B? Okay, it's already at the highest point, but it's its original point. It will have to go all the way down to the lowest point and come back to here to complete a wave. What if I start with M? Okay, so it will go up, down to the lowest point, and then it will end up here. So all this horizontal measurements is actually time, because it's using x-axis as time. So this time is actually a special time where the wave complete one complete wave. So it is time taken by each point on the wave to complete one oscillation. That's our period. Okay, then with this formula, whereby F equals to 1 over period, we will get what we call frequency. Frequency F is the number of vibrations a wave particle makes in 1 second. So this is a formula that you need to memorize. So what can you actually get from DT graph? Your amplitude and your period. And with this formula, I can actually get my frequency, because frequency is 1 over period. And the unit for frequency is actually hertz. Okay, so I've written here 1 over second is actually hertz, because frequency is equals to 1 over period. Yes, so you need to memorize this formula. That means from DT graph, I can actually get two things from my x-axis. Actually, strictly speaking, is one thing lah. It's the period from the x-axis. But with the formula, I can get another thing called frequency, because frequency is 1 over period. Once you have determined what is your period, you can then flip it and you can get your frequency. Okay, then now we'll combine these two graphs together. Remember, in DD graph, your y-axis, you can get your displacement and your amplitude. So it's exactly the same as your DT graph. The only difference is your x-axis. For your DD graph, your x-axis is distance. You can actually get your wavelength, right? It's the distance, horizontal distance between your crest to the next crest, or trough to the next trough. And the SI unit for wavelength is meters. Okay, now we have meters and we have seconds. We put them together. Meters over second is actually unit for speed. So speed is actually having a unit of meter per second. Now, how do we get meters? We can get it from our wavelength. How do we get seconds? We get it from our period. So we have this formula to find the wave speed. Okay, is equals to lambda over t. But I don't really like to have fractions. And remember, since frequency equals to 1 over t, okay, I can replace this formula with, I write it like that, right? Then, because this frequency equals to 1 over t, I can have v equals to f lambda. Then I have a very neat equation whereby it is, there's no fraction. So v equals to f lambda. Okay? So there you have it. This is how we get the formula for wave speed. Okay, So you can read through the notes here. Displacement DD graph gives the amplitude and wavelength of the wave. Okay. DT graph gives the amplitude and period, and then if we use formula, we can calculate frequency. Okay, I don't know if you can understand this. DD graph shows the displacement of all particles at a particular time instance. That means it is like a photo of many particles. Whereas DT graph shows the displacement of one particle for the whole duration. That means it's actually a video. Okay, and good thing you don't need to know what is the gradient of the graph. Okay, so recall and apply the relationship speed of wave equals to frequency times wavelength to new situations or to solve related problem. So because we have already learned V equals to F lambda, let's try over here. Okay, at a particular instance, a transverse wave of frequency 25 Hz, so this is my F, is traveling to the right as shown. At that instance, the displacement at point X is 0, yes, because it's on the start line. Okay, for Y, it is here. Okay, so what is the shortest time elapsed before the displacement at point Y becomes 0? So as you can see, so you need to predict for point Y, when will it become 0? Okay, the shortest time elapsed. So how will point Y be moving? Remember, this is a transverse wave. Transverse wave, what do you think of? Perpendicular. You think of perpendicular, yes? That means if the wave direction is traveling to the right, the particles will be moving either up or down. Okay, because this is a transverse wave. I hope you got this. That means Y will actually be moving up. Okay, I do not need to draw the next wave because for Y is too simple. It is at the lowest point. The next motion definitely has to go up. That means it will go up. Okay, but now, how does it actually complete a wave? Remember, for pendulum, it's like that, right? Pendulum. How does it complete one oscillation? If I were to start from X, X to Y, Y to Z, Z to Y, Y to X. So how many steps does the pendulum actually take? It takes 4 steps. It takes 4 steps. Okay? But how do we apply this to our wave? For Y, it will go up. But does it complete one wave? It doesn't, because it's at the lowest point. This is the original point. It is the lowest point. It will actually have to go up, right, in order to complete one wave. 1 step, 2 step. But after step 2, has it completed a wave? No, it just means that it went from the lowest to the highest. Remember, in order to complete one wave, I draw out this. If I'm here, okay, how is it that it complete one wave? It must go to the highest point, go down to its original, go back to lowest, and then go back to its original. So in fact, you'll take 1, 2, 3, 4 steps. So here, it has only completed half a wave because it has only go 1 step and 2 steps. So after that, the particle has to go down 3 steps and then go down 4 steps. So in order to complete a complete wave, okay, I call this a 4-step thing. It's stemming from your pendulum. Okay, so we should apply this 4 step. Okay, it's gotten a bit messy. Let me clear it up first. Okay, then we can try this again. Okay, for Y, it's here. It goes 1 step, 2 step, 3 step, 4 steps. For X, for example, if it does go up, that is 1 step to the highest point. Next step is 2, then it goes down 3, then it goes back up 4. Okay, so this is the 4 steps that you need to master. Okay, so when coming back to this question, the shortest time elapsed before the displacement at point 1 becomes 0. They want the shortest time, so it's only going up this way where the displacement becomes 0. So it would only take 1 step. Okay, but what are we supposed to find? We have frequency of 25 Hz. with this I can find period, because period is 1 over frequency, so it's 1 over 25. So I'll get a value of 0.04 seconds. Now, period is the time taken to complete one wave. And in order to complete one wave, I will need 4 steps. But now, for this question, in order for y to just have a displacement of 0, it will only take one step. Because 4 steps need 0.04 seconds, one step will then need 0.01 second. Okay? So this is something new. You have to think about the 4 steps. You have to use frequency to find your period, and you have to see from your question how many steps does y need to take before it has displacement of 0. It's actually 1 step. Okay, then from your period, which is actually the time taken to do 4 steps, you break it down into the time taken to complete 1 step. Okay, let's try D2. We have displacement distance, DD graph, and DT graph. So DD graph, this one I can get wavelength, this one I can get period. Okay, now they want us to find the speed. Speed is v equals to lambda over t, or v equals to f lambda. Okay, and we look at the options, all have cm per second, so I don't need to change my wavelength to meters. So if I look at this, if I choose this, it completes one wave at here, so the wavelength is 2 cm. Okay, if I don't want, I use somewhere like here, which is 0.5. Okay, so to complete one wave, it ends at 2.5. I will still get a wavelength of 2 cm. Okay, now let's look at the period. Period is the time, look at DT graph to get period. Period is the time taken to complete one wave. One wave is like that, so it will take 0.04 seconds. Okay, now we can use this formula, v equals lambda over t, 2 over 0.04. I will get a value of 50 cm per second. Okay, so this is how we apply v equals f lambda. This is how we get information from DD and DT graph. Okay, now this one. Diagram below shows the displacement position graph, displacement position, and is in meters, so this is actually our DD graph. It's a transverse wave at a point as it's traveling from left to right. Okay, which of following correctly depicts how the transverse wave would look like 1/4 of a period later. 1/4 of a period. One period t, okay, it involves 4 steps. Okay, but now they want 1/4 period, that means it's only 1 step. Meaning, this guy, I know he will come down, right? This guy, he will go up. This guy, come down, this particle. How about this particle and this particle? Okay, so if we can solve this, we can be able to find our answer. So, now this is direction of travel. I need to know how particle at 1 and 2, how do they behave? Right, whether they will go up or down. Okay, so I have to draw the next wave. Okay, let me erase everything first. To draw the next wave based on the direction of travel. So next wave will look like this, because it's going from left to right. That means I need to draw the waveform slightly to the right. Okay, and indeed this particle, he will go down, right? This particle, you draw a vertical line, it will go up. How about particle 1? It will actually go up. Particle at position 2, he will actually go down. That means after 1 step, this particle will be here. After 1 step, this particle will be here. How about this particle? It will actually go down, so will be here. So I will draw the graph. This guy will be here, and this one will be here. Okay, this one will be here, right? So we will need to look for a corresponding. So this is after 1 step, right? Okay, I repeat, this guy actually came down here. Yeah, This one actually moves up. How do I know? Because I drew the next graph. This one actually went, this guy actually went up. Okay, so that is after one step, because they want us to show how the wave will look like 1/4 of a period. 1/4 is actually one step. So the answer will be C. Okay, so this question is quite tough. Please try to do it yourself. Okay, because of few concepts, you need to know period is 4 steps. 1/4 period is actually one step, right? And you also need to know how the points will look like, right? If the wave is going from left to right, that means you have to know how to draw your next wave, then draw vertical line to see where it cuts. Okay. Okay. Next concept I will cover in the next video. So this is video 2.